I hope our introduction to the fluidized beds and fluidized bed technology was simple enough for everybody to get the basic understanding and idea. Now we are going to go for the applications, and of course, one of the most common application is combustion. That is the primary reason why this technology, fluidized bed technology, is advanced to its level that we see today. So, basically, we talked about two different types of fluidized beds. They both, I did not mention it to you yesterday, but needless to say, they both operate at or under atmospheric pressure. There are fluidized beds, and we're going to touch on them later on, that are pressurized, but the ones that we're talking about today, they are both bubbling beds and circulating beds. They operate under atmospheric pressure. Okay. In the bed case, again, you'll remember that any air that is in excess of minimum fluidization travels through the bed in the form of bubbles, and they enlarge as they ascend, and sometimes they coalesce, they get bigger, or they are the ones that promote some sort of mixing in the bed, dense bed, and above the dense bed in the freeboard region, they erupt and traject particles into the freeboard. In the case of circulating fluidized bed that operates under the fast fluidization regime, no longer bubbles there because it passed the turbulent stage, and you have dispersion of particles and clusters. Okay, in both cases, we can assume that these are reacting flows. That means there's a mixture of fuel and air reacting in these cases. Okay, so let's start with the bubbling fluidized beds. Again, the particles there, let's say the inert bed material is sand, and the fuel, a solid fuel, is fed into the bed. Um, this is from historical perspective. They are most, of course, plausible to use when fuel is solid. Okay, to burn a solid fuel, let's say a stoker, where you have a mass of fuel sitting there, you don't get the full benefit of contact. In other words, you don't maximize the air or oxygen to surface area combination. In a fluidized bed, this is a lot better, and then you can then burn a variety of solid fuels from um, coals of low calorific value to biomass or waste or even sewage sludge in these cases. Um, so this is the basic idea. You burn it either in a bubbling bed, which is here, and this is what we are covering. I want you to pay attention to the temperature, operating temperature range. It's between 760, well, this is not, could be as high as 900, but we don't want to go there. So usually in my designs, I always keep it at 850, which is a safe value for a variety of reasons that I will expand on more. Particle size, again, it could be different particle sizes. Um, and You have to understand that in this environment, uh, you don't really need to have perfectly round particles. By the attrition effect of the bed, particles, if they have sharp edges, whatever, they break off. They're filed off, and they become almost spherical. You can use lower fluidization velocities. Why is it important to use lower fluidization velocities, then you don't have to have very large blowers because these are high capacity, high pressure blowers. They're very expensive as a capital cost, but also a very expensive to operate. It requires a lot of electricity. But nevertheless, you can reach high heat transfer rates and efficiency, and they are less sensitive to the fuel moisture. Um, you will say why? Because I pointed this out later on. You have a large thermal mass here. Once the bed is running, combustion has taken place, and it reaches a steady state. Uh, Whether the fuel moisture is 20% or 25% won't make a big difference because you usually have 5% fuel, 95% bed material. So in this large thermal mass, it won't affect the overall temperature. Okay, and overall temperature is important, of course, to keep it efficient. In circulating fluidized beds, we can try a little higher temperatures. Of course, fuel particles, they could be around even larger, given the, of course, a transition velocity and to fast fluidization. You will have to use higher fluidization velocities. Uh, but this, of course, given the nature of this configuration, you can burn much larger amounts, much larger amounts of fuel in a continuous fashion. It's a lot easier for ash removal and other things, especially, and I'm going to touch on sorbent utilization. So here, a quick summary of parameters around bubbling fluidized beds and circulating fluidized beds when it comes to combustion applications. Okay, as you could see, one of the last point I mentioned, there's no solid circulation for bubbling beds, even though it can be forced, but in CFBs, it's more natural, and you can adjust how much you want to do. Okay, so this table will give you, if you were to design one, either bubbling fluidized bed or circulating fluidized bed, it will give you the operational ranges that you can start from. No design will be finite in the beginning. You start with these conditions, you pick the ranges, you go design it, iterate, come back and fine tune it until you have confident design. So before we go further, I think it's important to remind our basics in thermodynamics as to where we place, what's the place of either bubbling bed or circulating fluidized bed in this total thing. You'll remember your simple Rankine cycle, that objective is to produce high pressure, high temperature steam that could be fed into a steam turbine, will expand there, and then turn a generator, and the generator will, of course, produce electricity. Then the low quality, low pressure steam is condensed in the condenser, and then its repeater pumps. Okay, I should also remind you that the most inefficient part of any of these cycles is, of course, the condenser. That because of this, the maximum efficiency is limited. Let's say in good case to 42%. That means if you burn 1 kilogram of fuel cycle, you only get to utilize 40% of it in the form of electricity. The chemical energy of the fuel is only converted into electricity as 42% or 40%. So just I want you to remember this, and our objective is to use a different type of boiler that could maximize at least the combustion efficiency. So, since most of the fluidized bed combustion applications, in most applications, coal is the fuel. I think we'll spend a few minutes on what is coal. It's an evolution, of course, over thousands and thousands of years. It comes from plants to peat to lignite. Under pressure and heat and time, it becomes coal, and that we know it as a different, like in four categories. Anthracite is the kind of coal that has the highest carbon percentage. Bituminous or subbituminous are the coals that are mostly used in power plants. And lignite is the worst type of coal, as you could see from the chart, that has a lot of moisture and a lot of ash. But nevertheless, in very many countries, because this is it's available and it is used, it is not the ideal fuel, but nevertheless, it's used widely, causing a lot of environmental issues, of course. Okay. So, one final thing, if you divide a coal in four parts, fixed carbon is the part that will give you a char combustion. Volatile matter is the gaseous matter that under heating conditions or under pyrolysis, it will be released. Then the remainder, of course, moisture will be moved immediately whatever it is, and then the remainder will be ash, okay, which has a variety of materials. Okay, so again, before we talk about a fluidized bed combustor, let me just take you to the most common furnace or boiler in the world, that is a pulverized coal-fired power plant. Okay, in this case, you think of your car. In the car, you have a fuel injector. The idea of the fuel injector is to atomize a liquid fuel into a mist to give you the largest amount of surface mass surface ratio, or volume to mass to volume ratio, which is represented by surface area that is exposed to oxygen, to give you the highest combustion rate. In this case, pulverizers, they mimic atomizers. Coal goes through a number of physical processes, sorting, but then they go through pulverizers. They are extremely hard carbon steel made of that, and it breaks coal particles in around between 20 to 40 micron size. It has to be very fine because it has to be injected together with the air into the combustion chamber. I want you to pay attention to here what kind of temperature range. Stable fireball in the furnace coming through various injectors, and the optimum temperature of operating pulverized coal furnace is between 1500 to 1700 Celsius. Okay, and as a result, you have nitrogen oxidation which is abundant. You will ask a question: why is there so much nitrogen oxides in the form of NO2, and we call them NOx, NOx? If you look at proximate analysis of a coal, you will notice that there is some nitrogen, but that's not the nitrogen that gives us nitrogen oxides. At this higher temperature, you may check in your textbooks, or you may check with your professor. Something's called the Zeldovich reaction, which is the fixation of atmospheric nitrogen that is released and that nitrogen reacts with oxygen to give us a lot of nitrogen oxides. Then, what is the problem with nitrogen oxide? Same thing you will ask with sulfur oxides. As they are being released, of course, the hot gases are cooled as it pushes out of the stack, and when it reaches a cooler level, together with the moisture in them, they become liquid. So come back to Earth in the form of nitric acid or sulfuric acid. That is the problem with having a lot of nitrogen oxide. Not just with this, it applies. Same thing with automobile engines, especially with very high compression ratios, high temperatures. Then forces us to use catalytic converters either for cars or for power plants. So this is your something to keep in mind that will justify why then fluidized beds will be preferred over a pulverized coal fired plants. You may remember from yesterday that I said this was one of my first tasks in India, to come to India and help. We partner was the Bharat Heavy Technologies to convert those very bad polluting primitive pulverized systems to CFBs. So if you compare them, that fluidized bed is an alternative. We have an efficient combustion system. You have a much broader range of fuels. You can burn in fluidized beds. Operates at lower temperature. Again, it's a big advantage, especially from NOx perspective, and it also have as an integrated sulfur capture in a combustion chamber. What does this mean? You will see in a minute. In any other system, pulverized system, sulfur oxides occur. They are formed, and unless you have a flue gas desulfurization system above your plant, it's released in the atmosphere. In a fluidized bed, by using sorbents, we prevent sulfur oxides from happening in the first place. So we don't need to clean it because it doesn't form. So again, to review, the Q features is the fuel flexibility, that you can burn coal, biomass, or waste materials. More complete combustion because of one of the things is higher residence time and a high thermal efficiency. As I said, captures NOx and SOx, and heat recovery is much higher in this case. Here is these are two existing industrial boilers. One is a bubbling bed. This is the bubbling bed part. This is solids recovery, heat recovery part, but also part of return system. Whereas this is the CFB. This is our riser circulating bed, and this is a cyclone that captures and recirculation happens here. And of course, a lot of heat recovery takes place here from the hot gases. We have, as I mentioned, three primary designs. It could be a bubbling bed, it could be a circulating bed, and it could be a pressurized fluidized bed. We're not going to spend a lot of time on pressurized fluidized bed. There are still a lot of research taking place to better understand a lot of things. But if it's pressurized, then you can use it in combination. Part of it as a combustor, part of it as a gasifier. Then, since it's pressurized, it can be connected to gas turbines, the pressurized gas, whereas the steam could be connected to a steam turbine. So much higher efficiency, but of course a lot more expensive to build and a lot more expensive to operate. We're not going to spend a lot of time on the pressurized fluidized beds because a time limitation, and second, it's still in the development stage. Again, we know most about bubbling beds. I Most of my designs of the bubbling beds, they were for biomass applications, but mostly for gasification type. If we I wanted to, some of my bubbling bed designs for simply for incineration purposes, so that waste or some agricultural biomass that could not be gasified could be burned to get rid of. So, principles of operation in these: find solid material like sand or coal. You put in a container, high pressure air. We blow it, we fluidize it, and it achieves a fluid-like state. Um, and of course, we enhance efficiency and use it for various types of fuels. So I mentioned that again. I repeat, this is one of the design considerations. These are all approximate. These are all based on experience. You use 5% coal to 95% inert bed material. Then in this case, it could be ash or sand. And we are talking about steady state operations around here. So again, lower temperatures than pulverized coal furnace. And let's talk about sulfur emissions. Okay. Um, Let me see if I'll go here. You see in this diagram, you have coal here being fed, and then you have limestone here mixed at a certain ratio into the combustion chamber here. Okay, this is a CFB. Now I go back. I should remind you, one of the critical advantages is in fluidized bed combustion, there is no need for pulverizers. Pulverizers are very expensive. They have to be maintained uh, regularly because they are constantly grinding coal particles, and then they have to be fixed, replaced, and all of those. And they consume a lot of energy in doing that. There's no need for pulverizers in fluidized beds because the particle size is much larger, as we will touch. Okay, but let's go to the emission control and when it comes to sulfur. So we use limestone. What is limestone? Limestone is calcium carbonate. Okay, calcium carbonate does not directly interact with sulfur oxides. You have to calcinate it first, and calcination takes place under high temperature, base a certain temperature range. That becomes calcium oxides, which unfortunately releases carbon dioxide in addition. So it has to be if you examine a limestone particle under a scan electron microscope, you will see a really porous structure within it. The more porous it is, the higher the capture efficiency because it has a lot more surface area. It's not just around the particle, it's within the particle that gases interact with. Anyway, calcium oxide and sulfur dioxide, they react, giving calcium sulfate, which is a solid material now, which can be extracted from the bed. Okay, this is the beauty of being able to do this. You cannot use this in pulverized system A because of a very high temperature, because of the size, and because of the short residence times. Okay, why is the temperature? If the temperature is above a certain level here, you basically bake the calcium oxide particles, and then you don't get the benefit the porous structure. And it's like you bake it. It's just the surface that is in contact with it. So, um, again, when it comes to heat capture, I touched on it yesterday. Boiler pipes can be placed within the bed with refractory preferred, but if you don't do this, you will encounter pipe erosion because of constant impact of solid particles on pipes. So we had a look at this before. Uh, so you have basically coal preparation here. It goes through some sort of, after it is mined and brought to the site, it goes through a crusher, but crusher is not the same as pulverizer, much larger size, and it also eliminates some other non-coal particles. There could be some metals in there, and it goes through magnetic separators, and here you have coal being fed. As I said, at a given ratio, limestone particles are introduced. Now, the mixture, of course, this is utilized, is pushed in there pneumatically, and then you have your a boiler here, and provide the primary air, and then secondary air for again, we talked about the secondary air to provide the kind of complete combustion here. This is operating under fast fluidization regime. That means all the solid particles are entrained out of the bed. They're captured, cyclones, and then returned. That's why it's a circulating bed. And then the rest is part of the steam power plant operates. Okay. Uh, uh, so you have to have higher fluidization velocities. Um, the other thing I should mention, okay, which is a disadvantage to pulverized boilers. So in a combustion application, um, you you need to determine, here is my fuel. In my fuel, I have this much carbon, I have this much hydrogen. These are the main combustibles, okay? And you calculate your stoichiometric air requirement. Then, to ensure more complete, stoichiometric amount is a theoretical amount. So to ensure complete combustion, you add more air than the stoichiometric amount. With pulverized systems, because of very high surface area ratio, you don't need to use a lot of excess air, because excess air, as the name implies, is just excess air. And even though it promotes complete combustion, it is lost through the stack, and it carries with it a lot of thermal mass. You can capture some of that, but only at certain level. Otherwise, you'll be condensing the flue gas, and if it's condensed in a liquid form, it will destroy the stack and everything under it, because it will come down in the form of acids, as I mentioned. So, in fluidized beds, you have to have much higher excess air, because of the mixing process is not as rigorous, as violent as it is in pulverized systems. So this is a disadvantage. And nevertheless, this is the particle size range, and it is still efficient, because it provides, as you can see here, much longer residence times than PCs. If there is unburned carbon here escaping, we capture it back through cyclone until it becomes ash. And it's ash particle, it's lighter, and we can separate it much easier through separators. And the another beauty here, just pay attention to this: 90 to 95% sulfur removal from coal. If you ever to design or take part in designing a power plant, you will see that when you use especially high sulfur coal, and of course nowadays you cannot not use a flue gas desulfurizer, they can be as expensive as the total plant. They are very expensive, especially if you're added on to an existing plant. So the advantage of this limestone is very cheap. Limestone is very cheap, and also the beauty of it when you capture sulfurs, it's not in gaseous form. It is captured as calcium sulfate, which is in. Hey, are we doing okay? I hope so. I can't see you, so I'm assuming we're doing okay. So, what is next then? How are we? Who is using this? A lot of countries, especially even though this is developed in late 1980s, we had a number of demonstration plans in the 90s, and a lot of utilities started using this, especially in countries like the U.S., Canada, India, China. It is used significantly, and so various sizes of power plants, not as large because of the throughput ratio, but the one that I was involved in design was 165 megawatt electric plant that is still in operation. Let's again, we talked about efficiency. In this case, we use fluidized bed. You have total overall maximum efficiency of the plant at around 43%, which is ideal, better than PCs. But if PCs are supercritical, again, you should know what supercritical boiler is, and then it could be higher. Emissions are a lot more favorable in this case, and the fuel flexibility is superior when you are burning a variety of low grade fuels, especially. Okay. Um, I so far I kept talking about power generation, uh, that you use coal, and sometimes you co-fire coal with other fuels. Co-firing means you mix, let's say, coal with biomass, or there is something called, for example, petroleum coke. It is the sludge after the catalytic cracking. You can't burn it by itself. It can contain a lot of nasty stuff, but you mix it with coal. So depending on the application, you can mix it with a lot of things. So it's called co-firing. But it is ideal, especially if you have a large amounts of municipal waste, and the only way to get rid of this is through incineration. Then you can mix it with coal and burn it in CFBs. Um, all right. What are the challenges when you consider, again, like the room you're in? Okay, the size of the room could be the plenum chamber of a bed. It's that size. So to achieve a proper fluidization in such a geometry, large geometry, is extremely difficult. And the graph, the schematic I showed you, it had a partition in it, which divided the bed into two to ease that mixing or better fluidization. Stability of combustion becomes an issue, especially if you have slugs being formed, which is possible, or the agglomeration of ash. If the ash is at a higher temperature, and it is that temperature is, if not, it is not well controlled. Um, Ash particles become soft. When they are soft, when they touch each other, they start agglomerating, and when you have those big agglomerates, they result in defluidization of the bed. So when you have a bunch of them, the drag force then cannot overcome the gravity force. They start sinking, and then you lost the bed. You lost the bed. You can even destroy the whole reactor. Bad material handling, again, is complex. It has to be sure that is properly fed to the bed. So these are some of the operational challenges that you should be aware of if you're designing and operating such a system. It's just quickly, it shows you again the operational or design history of, starting in, I mentioned the Winkler process, but very quickly, many countries, it's been adopted and successfully used. So next thing is, I'm going to go through this a little quickly, and part of this will be, as I'm going to use it as an example, tutorial example for you to see how we we use these as part of our design of a system. So, fuel preparation, as I said, is a challenge, is essential for a successful and efficient operation of combustor. Key processes that we need to make sure that they're optimized. Um, Sizing is important. Even though I said a lot of they're versatile system, flexible, nevertheless, the more uniform the size is, the better, the more uniform mixing and fluidization will become. In a lot of cases, drying is important. It Fuel comes from various sources, and they come with different levels of moisture. We promote a little bit of moisture, but not a lot, because nevertheless you'll use the exothermic energy of your system in order to evaporate the fuel, or moisture, bring it to 100 Celsius and evaporate it out of the fuel. We want it to evaporate, but because of it, as it evaporates, it opens up the pores inside the fuel and allowing for oxygen penetration in there. But when you have a lot of it, it remains there too long, and it inhibits oxygen penetration in this case. So drying is important, and as I said, separation of non-combustible materials is important before it's fed into the side. Sizing, I mentioned already, but we can use up to even like 25 millimeters. 25 millimeters is like 2.5 centimeters. This is huge advantage compared to pulverized systems. And drying is itself is an integral and essential part of fuel preparation. So, to summarize, separation of non-combustibles, fuel preparation of different fuels, and then we will see, you'll have to determine, depending on the amounts, on this impact on combustion efficiency. Um, we already talked about this. Let me just talk about on the design considerations. So to accommodate fuel flexibility, our system, the CFB system, must have adaptable combustor designs. Robust fuel feeding system, that means it is adaptable when you have different types of fuel coming, and one day it's pure coal, the next day it is mixed with municipal waste, and also you have to have a proper emission control system to be able to adjust temperature, air, and also sorbent amounts. Okay. This is a very useful chart that will give us a good understanding of what kind of fuel we should use that will give us the amount of calorific value. At the end of the day, one of your key objectives is per unit mass of fuel, how much heat you will extract from this reactor that will be converted into high pressure, high temperature steam. You have to calculate that amount so that you will know exactly how much electricity you're going to produce. So this chart is very helpful to figure out which ones are part of the standard design, which ones will we don't have enough operational experience, and you will need more probably pilot scale tests before you can use it in a fluid bed. Okay, so we talked about this as well. Um, I'm also watching the time. Efficiency in, as I said, is important. Um, Need this. Again, I'm sure that you know these concepts, but let me remind you again. When we talk about efficiency, first is the combustion efficiency. Combustion efficiency, how much of the fuel you have converted into a thermal energy. So how much of the chemical energy has been now converted into a thermal energy. That is out of combustion efficiency. So as I said, it's very high in a fluidized bed. And then you have the boiler efficiency, and the boiler efficiency, how much of that thermal energy you've been able to transfer to the boiler or in the form of steam. Again, it depends on heat transfer surfaces. Um, I'm assuming that you're able to see me when I show you something object. So when you have this tube, this is a heat transfer surface. Water is going here or low pressure steam and coming out as steam or high pressure steam. When this is in an environment that is very dirty, you have a lot of ash particles and they are at a higher temperature than this one. They're coming and hitting the surface. After a while, you have slack formations or condensation of hydrocarbons that form soot over this. So, in some systems, for example, PC systems, you have to blow steam over these to remove that coating. Otherwise, it prohibits it, it prevents heat transfer. In fluidized bed system, the advantage of if it's you have sand particles constantly, it breaks off that slack over it. So it promotes better heat transfer, but at the same time, if you have a lot of contact, then erodes the surface and erupts the heat transfer tubes. Okay. Um, so with that, I was talking about efficiency. So we talked about boiler efficiency could be high, but overall thermal efficiency of the plant, because of what I showed you in the Carnot cycle example, because you have to condense the low quality, low pressure steam, then you lose a lot of the energy. Therefore, your overall thermal efficiency of your plant is very much limited. Um, Again, combustion efficiency, as I said, we can achieve up to 99% combustion efficiency in CFPs because if you have unburned carbon escaping the bed, you'll bring it back and then burn it to smother and until it is a fine and light ash particle. Okay, I explained these, improving efficiency. We can do all kinds of things in order to reheat cycles, economizers, and everything. But this is beyond our scope. But to give you again a good comparison, CFBs, you can use it for these kind of fuels compared to one bubbling fluidized bed application, and you have some thermal efficiencies. These are from operating systems, but I did not include the source did not include which ones it is because of the confidentiality. Okay. So emission controls, as I mentioned, it is crucial that we control three sources of emission. Talked about sulfur oxides, why it is. If you don't control it, it will come back in the form of sulfuric acid, horrible for the environment. It destroys forests and vegetation and everything, but it also destroys the power plant as well. Nitrous oxides, the same effect in the form of nitric acids. And the third one is particulates. In power plant terminology, it's called SOx, NOx, and ROx, as it refers to the particulates. So particulates, there is no, it's a completely physical process. You have to ensure that you have, in addition to cyclones, you have electrostatic precipitators and filters so that no particulate matter escapes into the environment. If it escapes, everybody ends up breathing it, or it accumulates on everything, including vegetation. So, if you want to design and operate in these modern days, a solid fuel fired system, you have to ensure the regulators that you have completely control these three pollutants. Of course, this is beyond our scope, but then you have to have other um, proofs of how do you control carbon dioxide, whether you capture it or not. That's a completely different subject. But in our case, ironically, the objective is to maximize the amount of carbon dioxide while minimizing the amount of carbon monoxide leaving the power plant. Okay, we talked about this particulate matter. Yes. So let's touch a little bit on the biomass. So far, we talked about mostly about coal. Now let's go to biomass as our fuel. So, as I said, biomass will come from various sources, whether it's agricultural crop waste. For example, you grow corn. A lot of the parts that are not used, it comes back as waste. If you, let's say, grow rice, very much like in India, and you're all familiar with, you have to dehusk the rice. What do you do with the husk? It's a byproduct, it's a biomass, or simply waste from a number of municipalities, including if you have a sewage treatment plant, the sewage, the sludge, they are all biomasses, and they come in with high moisture ratios. So every biomass combustor will have to have a drying either within the bed or adjacent to the bed, a dryer before it comes in there. So you have fresh biomass, it enters, you have to dry to a level, remove the moisture, for which you're going to spend energy. another is the gaseous matter. Under conditions or heating conditions, they will leave the and char, all the part much faster than the char, and then nevertheless you have oxidation of carbon that results in the form of carbon dioxide, and oxidation of hydrogen that results in the form of water vapor leaving here. Of course, the net effect here, this is an exothermic reaction. Heat is released, heat is captured, and it is utilized in one form or another. So let's go through this. This is part of our exercise to go step by step. This we are designing is still. We need to dry. Um, Drying. We're going to talk about later on specifically about fluidized bed drying. So the drying process here is the physical aspect of drying. It could be fluidized bed or it could be just an external dryer, but nevertheless, it requires energy input. You have to incorporate this into your calculations that you have to predict or determine. There are ways, of course, to do a moisture analysis of your fuel. Then you will know that part of your energy that will be released from the fuel will be taxed to evaporate that fuel, the moisture above at 100 Celsius evaporation temperature. If you don't dry the fuel properly, it will inhibit combustion. It will result in premature combustion, and because your fuel is only for so long in the bed, it will. If it takes too long for it to release its moisture and then devolatilize and then burn, then it will occupy a lot of space and time, then your throughput will not be very high. So those are important factors to consider when drying. So there are various ways to predict that through modeling. The heat sink approach is very easy. It's limited by heat transfer, and all the heat is used to evaporate. Then, straightforward one is a zero order reaction model of Arrhenius that I prefer using it over the other two. An equilibrium approach is assuming the water vapor and liquid moisture are in equilibrium within the particle. So, which is more accurate, but Arrhenius is a lot more straightforward. Uh, and it just gives a little bit more detail in how we use this. Heat sink approach, useful for fluidized beds where internal heat transfer resistances are significant. Nevertheless, for numerical modeling, as I said, this gives us a linear approach, which I prefer because it reduces computational time and calculations are more straightforward. Let's pass these, we will talk about. So, a little bit more better understanding, which will be helpful for our lecture tomorrow or the day after. So, in a particle, when you're drying it, as the moisture evaporates, it shrinks. Okay, so how much do you need to do this? This is your temperature moisture diagram. So here you're increasing the temperature. It moisture remains because it has to come to that boiling point, evaporation point, after which it starts dropping, and you reach a point where you're no longer able to remove the surface moisture because the rest is diffusion controlled. When it's diffusion controlled, it is independent of temperature, as you can see. Regardless of how much you increase temperature, it flattens out. So this is the point that you need to model. This is why we're trying to model. This is the point that you need to determine at which point that you no longer you need to dry it. Leave it because you have removed this part. Then the rest will be diffusion controlled, and as I said, in some cases it will enhance combustion, but nevertheless it slows down the burning rate. Yeah, so different equations as to how you determine the amount of moisture removed, and all of those. Let me pass these. Let's get to the second stage, devolatilization, means release of the volatile matter out of the fuel. Okay, so those volatile matters, okay, it's the gaseous ones, and the burning it burns much faster, and it usually with biomass, it can be up to 80% of the total weight of the material. So it's significant. Why am I saying this? Because you have to understand that when the volatile matter is burned, it is much faster. Therefore, a lot of heat is released at that time. You need to be able to capture it. The remainder is char particles, and char is the solid part, which burns much slower. And this is the part, if you're using a CFB, you have to ensure that it is recirculated. So you have to configure your heat transfer surfaces in a way that it is able to capture the heat from the combustion of the volatile matter and also heat release from the combustion of char, which is in a much larger happens in a much larger time frame. So this is for that part. Then how do you uh, control the kinetics? How do you determine the kinetics of biomass and pyrolysis, of course, initially? In any biomass, it is not a homogeneous thing. It's not just this or that. It is quite heterogeneous and includes natural polymers, cellulose, hemicellulose, and lignin, and they each decompose differently. Okay, burn differently. So in our treatment, however, simplest approach is to say, to heck with it. We assume that it's homogeneous and everything happens at the same time. So you use Shefizadeh and Chin's model that you have three parallel, but they're first order reactions, okay? And then they're transforming, if this is, for example, a wood particle, transforming it into a gas char. And of course, a consequence of this is tar, which is, I haven't mentioned it so far, one of the biggest disadvantages of biomass that you have to, especially if you're gasifying it. Combustion is at high temperature, we don't need to worry about, but if it's part of the pyrolysis problem, tars are formed, you make sure that it is burned. Anyway, three first order reactions you do this. You use the global constant for overall fuel conversion, and you use the de Blassie's activation energy within the temperature range of what you're doing. Okay, so we were talking about combustion of volatiles, and obviously, when we say a volatile matter, it's predominantly carbon monoxide. Comes from the pyrolysis part or incomplete combustion of carbon, and of course, hydrogen. There are some others, but these are the two main combustibles. And it represents, as I mentioned, a significant portion, between 50 to 60% of the total energy released. In some cases, it could be even more during biomass combustion. Needless to say, uh, when you are burning something in your furnace or a combustor, you will have it analyzed in the lab. So you will know exactly the chemical composition of that fuel so that your calculations will be very accurate. Um, and the reactions, of course, pyrolysis and volatile combustion, which will follow pyrolysis. Basically, at the end, you see carbon monoxide. Where is my cursor? It's here. Carbon monoxide reacting with half an oxygen, of course, giving carbon dioxide, hydrogen, giving water vapor. Basically, hydrocarbons, when they react with oxygen, they will give you carbon dioxide, theoretically, of course, and hydrogen and water vapor. There will always be some carbon monoxide present, escaping unreacted because of the nature of the reactor. So when you look at it and a fluidized bed part of it, um, where are the exact, remember I said you have to determine your locations of your heat transfer surfaces precisely. So bubbles, the volatiles form bubbles, okay? They will be in the bubbles because they are part of the process in bubbling bed. Around biomass particles, when you have bubbles, they're not reacting directly with the fuel, they will rise to the bed surface. So within the bed, mixing is poor because the bubbles entrap these volatiles. When they're entrapped in there, they're not mixing to the bed and burning. Okay, so major combustion will take place as the bubbles burst and mix with oxygen. So this is just for the volatile matter, okay? That means you have the bed, dense bed, the freeboard, then you make sure that you have proper heat transfer surfaces in the freeboard to capture the heat that is released from the combustion of volatile matter, okay? With char, it's a different story. So what are the factors affecting volatile combustion? Temperature. The higher the temperature, better the combustion rate, but you know the limitations of temperature. Gas velocity, again, as I mentioned, it promotes better mixing, but it costs you. And bad material, make sure the inert particles, the more inert particles, non-combustible particles you have, the more tax you will pay in the form of heat loss and, of course, ignition delay. And but you can also add some other materials that can enhance combustion in addition to your fuel. Okay. Um, what are the challenges? Incomplete combustion, which is usually the case, as I said, will end up in carbon monoxide emission. You improve mixing. So to improve mixing, you either put static mixtures or even forced, but they all, if you have static mixtures, it will nevertheless, it's an additional resistance, and static mixtures, they can cause fouling and other challenges. So it adds to the cost, but nevertheless, to achieve uh, better mixing, you need to either use more secondary air or use static or dynamic mixtures to promote mixing. Heat distribution is uneven. If it's This is caused by hot spots, and if you're not able to remove heat uniformly, hot spots that may affect not only efficiency but also the furnace life by causing weak points. Again, make sure that your bed design will have uniform heat removal. And we talked about kinetics and other things. Now let's turn our attention to char combustion. Char is what is left as fuel after the volatiles are released. It's much slower, it's combustion. This is the longest step, and you have to, which will determine, of course, your solid recirculation as well as the reactor side for a very simple reason, ensuring that you have long enough residence time. Okay. Uh, this is a fundamental thing for any combustor. Okay. To achieve a maximum combustion efficiencies, you have to pay attention to what we call three T's: time, temperature, and turbulence. The higher they are, the higher the efficiency. But as I said, you cannot keep it too long there, otherwise, you're preventing fresh particles coming in there, and your temperature cannot be too high. Then you lose the advantage of a fluidized bed. And the turbulence, you have to pay for. Turbulence is good, but you have to pay for it in the form of more air. So, but if you have them, then you will achieve them. Then these are the again basic reactions. Now, carbon reacts with oxygen to give carbon dioxide. The steps are first it's carbon monoxide, then carbon reacts with carbon dioxide as well, or it reverses into carbon monoxide through a Baudard reaction, and then carbon and water. This is the water gas reaction, water ship reaction that releases hydrogen. So this is a continuous process that is taking place. Okay, leave that too. And yeah, we talked enough about charcoal combustion. Okay, this is all I wanted to share with you. I want to talk about within our limited time about the application of fluidized beds for the combustion of solid fuels, which are predominantly coal or biomass. I hope you had a very basic idea about the process, basic idea about operation, and basic idea about what should be considered for a design. There is no way that within how much information I was able to give you and you have in your possession, you can go and design a fluidized bed combustor, but at least you know where to begin. You know how to do this. People who do these kind of things, they are, of course, they have amassed many, many years of knowledge and experience, but nevertheless, this is just, we just scraped the surface and there is a lot more depth under the surface. Okay. Uh, I stop here and I wait to see if there are any questions. If not, I have one example I wanna go over with you, and that will finish this class for me for today. Okay. So, any questions? Yes. Not fully, but I could only capture half of it. I think it just went in and out. So if you could just speak to the microphone so I can hear better. Yes, much better. Yes. Mm, yeah. Yes. So, very good question. Both options are possible. In some cases, we use the fluidized bed as a combustor, but everything I say is steady state. When you start from cold, it's a different operation. You will need to have a secondary fuel like propane or natural gas or liquid to bring the bed to the operation temperature, at which point you can start feeding the fuel. Okay. So in one scenario, it's just a combustor. You are feeding a already dried fuel into it, and you're extracting some of the energy of this, giving it to an external dryer, removing the moisture up to a certain level of the fuel and feeding it into the fluidized bed. In the second option, the dry air is already it's within the bed. You adjust the batch size accordingly to make sure that you have enough time to dry the fuel that goes into. So you probably, like, for example, you can partition the bed, okay, and as it dries, it weighs less, and then it goes over the partition into the combustion chamber. Okay, so these are all possible designs, but very good question. It's up to you, and it depends on the fuel type. Sometimes when the moisture level is really, really high, you want to dry it externally. Okay. Even you may use mechanical separators like centrifugal that you could push the moisture out, and whatever is in there, then you can use it, remove it thermally. Okay. So if you're using a bubbling bed, it's usually batch, okay? Unless you add another portion to it, but it's usually that because um, the ash removal is, if you're not successfully able to remove because they're lighter and you can capture whatever, but if they're slagging, they become heavier and you cannot drain it under the bed. It's a batch operation, but if it's a CFB, it's definitely a continuous operation. Okay. Hi. What say it again? So inert part. So as I said, what big advantage of a fluidized bed is it has a very large thermal mass. That thermal mass is deposited in inert particles. So you have to have that inert particles, either it's sand or ash, whatever, so that it provides you the activation energy of the fuel. Without which, so if you don't have it, like the bed in this case is the spark plug of your car engine. Okay, so the inert particles, they provide that activation energy for the fuel to combust. Okay, any more? Hi. It is important to maintain it, not only maintain it, but keep it uniform if you want to have uniform combustion across the bed and also uniform heat transfer. If it's not uniform, you will end up like in your heat transfer surface, unequal distribution of heat, which may result in a lot of problems and inefficiencies. So it is very important to ensure that it is uniform, and to for it to be uniform, you have to provide a very good mixing. This is one of the key elements of both design and operation of a successful fluid bed. So let me ask you, Professor, so have they seen an operating fluidized bed? Have they been to the lab yet to see how a fluid bed operates and how the bubbles interact with particles and all of those? Have they seen an operational fluid bed? Okay, but they have seen at least like a transparent fluid bed and bubble formation and all of those. Okay, good. All right. Thank you. Well, good morning to you. For me, it's what time is it? It's it's almost midnight. But thank you. I will remember you wishing me good morning tomorrow morning, okay? Very good. Overall, yes. There is a ratio, and in overall, when we calculate the plant overall efficiency of the plant, all the auxiliary powers, okay, they are incorporated into it. So, and they are nevertheless, auxiliary power consumption is quite small compared to the enormous heat loss through the condenser. So, yes, as far as environmental benefits go, I can't tell you how, like, I've done a lot of techno-economic analyses. With the exception of carbon dioxide removal, it is still the most economic, technologically superior, and economic solution when it comes to solid fuel combustion. Okay, but uh, if you have to consider carbon dioxide removal, then it applies to all fossil fuel, whether it's a natural gas, whether it's an oil fired, whether it's coal fired, they all release carbon dioxide. So you remember the chart? I said this is the Geldart classification, and you have the properties there. From that chart, you will realize that for a given particle size and density, this belongs to the group B particles. Okay, and with that, then to calculate minimum fluidization, I said terminal, but it should be minimum. I have two ranges of Reynolds number. One, if Reynolds number is less than zero point 0.4, we use the formula. They are all derived from basic formulas and also used, of course, the constants come from correlations from the experiments. And if it's between zero point 0.4 and 500, it's a very large range, but we use the second formula. In this case, I calculated the Reynolds number. I gave you the formula yesterday, and I found it to be almost 45. And if it's 45, it is within the range of zero point 0.4 and 500. I use the second equation. When I use this, I find the velocity. One 27 as 2.37, and the other one is 2.72. I'm sorry, this is the UT. So from there, this is again the Reynolds number definition, and this is further through correlations, experimental data by somebody I mentioned yesterday, late Professor John Grace. This is one of the most critical contributions that it is translated into this form, in which C1 is 27.2 and C2 is 0.0408. When you put those in there, and the Archimedes number, it's defined as this one. And when you plug them in, you find the Archimedes number is 2268, which gives us a Reynolds number at minimum fluidization at 1.65. This is for the gas, okay? And therefore, you have under ambient conditions a minimum fluidization velocity of 0.087 at 825, because of course different physical properties. It is further reduced. So even at lower velocity, you have achieved minimum fluidization. Okay, that means at these velocities, you no longer have a fixed bed. It will start fluidizing. Since this is a group B particle, minimum bubbling is the same as minimum fluidization. So as soon as the bed is fluidized, then the bubbles will form. Therefore, group B particles are difficult to handle. So if you can, don't. The easiest one is to use group D particles. Yeah, I calculated the turbulent before minimum fluidization, but I don't know what I did, but I everything got mixed up here. You can still hear me, right? Okay, so this was an example of very simple hydrodynamic calculation that you can start from there. Always determine the particle, which classification it fits into. And then from there on, there are large number of correlations, but it's the safest to use the Grace 1982 correlations. Calculate your Reynolds number, Archimedes number, and all of those. And from there on, you can calculate all the physical parameters that you need, bed expansion to transport disengagement height, and all of those for a given mass of or cross section of bed. I'm gonna stop here. because I'm out of gas. And I will recuperate again for our tomorrow lecture, which I think will be about on gasification. There are no other questions. I wish you a good, productive morning. And please also, how about this? Before we start tomorrow, think of anything that you want me to go over again before we start gasification, okay?